Very good. Let's see. Today's class, we will discuss the second law of thermodynamics. And the way to start this is to remind ourselves that Clausius had said something to the effect that the entropy of the universe increases. And that's a little bit vague because after all, entropy only applies to situations of equilibrium. So a better way to say it, and let's call our screen here, is to say something like, in an adiabatic irreversible process that starts and ends in equilibrium states, the total entropy increases. So it's crucial that you do not supply heat or remove heat from the system. It's irreversible, so it can go in any way you want. But the crucial aspect is that it starts and ends in thermal equilibrium. Under those circumstances, the total entropy increases. Now, if the adiabatic process ends up being reversible, which means that every single intermediate state is a state of equilibrium too, so that the actual process is infinitely slow because you have to allow a lot of time for equilibrium to be reached at each intermediate state. Then the entropy remains constant. So that's what we want to explain today. Now Gibbs came up with an addendum to this because according to the formulation above, the entropy tends to increase, but the formulation is not particularly clear about how much it increases. Okay, so the addendum of Gibbs is that the entropy increases to the maximum allowed value by the constraints that are imposed on the system. So what I will want to do now is talk about what this second law is. It refers to the fact that refers to the Clausius entropy, the thermodynamic entropy. So if you have a process, an adiabatic, irreversible process that goes from equilibrium at time t to equilibrium at t prime, then the Clausius entropy at t is less than the Clausius entropy at t prime. If the process were of a reversible process, then you would have the equal sign. So this is for the reversible process, that's for the irreversible process. So we want to figure out how this comes about. Now, the crucial element in this is the fact that the quantity that we know how to compute irrespective of thermodynamics is the Gibbs entropy. And so let's write the Gibbs entropy, and the Gibbs entropy is going to be minus the integral over all the microstates in phase space of a distribution, which is a function of the microstates, the probability distribution, log f of z. And the way it works is that at time t, at the initial time when we're starting the whole process, you're in equilibrium. So at that time, the probability distribution, f, that appears here, is such that it maximizes the entropy subject to constraints. So this is the canonical probability distribution. It maximizes SG subject two constraints. Now, depending on the problem, you can have different constraints, but let's imagine that the constraints are given by certain functions. Let's call x, which is a function of a microstate. So x could be energy, or it could be the particle density, or it could be whatever. So the constraints are going to be the expected values of these functions, and let us call them capital X. And this is the constraint. These are the values at the time t. And so at the initial time t, we have an entropy that is computed with the canonical probability distribution that maximizes the Gibbs entropy subject to these constraints. At this initial time, we are in equilibrium, and we have the following identity: the Clausius identity, the entropy, the thermodynamic entropy, is equal to the Gibbs entropy, that is for the canonical distribution at time t. So this is the beginning. Next, we want to figure out what happens when we go from t to t prime. So next, remove some constraints in the system. We're not talking about these constraints here. Well, it could even be one of those. But for example, you can imagine you have a container, and the gas is there is gas on the left, there is gas on the right, but there are at different pressures, there may be even at different temperatures. Now you remove a container and allow these things to move around. Or you could have your gas and you squeeze it. Squeezing it means you're changing the external potentials, right? A box is a form of a potential. You're changing the external potentials, you're performing work. No heat is exchanged, but you're performing work. Or you remove the piston out and allow the gas to expand. Or you can introduce an external electric field, or whatever. Remove some constraints, allow the gas to evolve, allow the system to evolve to a new equilibrium at t prime. Now, the crucial thing, and this is important, this process t to t prime is described by some Hamiltonian. The Hamiltonian may be just you allow the gas to expand freely, or you allow the gas to push on a piston, or it gets compressed. But all of these things are described by terms in a Hamiltonian. This process is described by a Hamiltonian dynamics. Crucial. What this means is that your canonical distribution at time t evolves through a new distribution at time t prime under the action of this potentially time-dependent Hamiltonian. But the whole evolution is Hamiltonian. Very good. The new situation is one of equilibrium. You allow the gas to reach a new equilibrium. But in this process in which the dynamics is being described by a Hamiltonian, we have that the original Gibbs distribution that described equilibrium at time t ends up being exactly the same as the new Gibbs distribution that describes that describes the new situation of equilibrium at time t prime. Now this is why is this? Well, remember how we even figured out the actual form of the entropy? We stipulated that if the evolution is Hamiltonian, then there is no loss of information. That's exactly what I have written here. Now, sometimes people say that this violates the second law of thermodynamics because the entropy at time t is not less than the entropy at time t prime. This does not violate the second law. And the reason is that the distribution that we have here is not a canonical distribution. This is not the canonical distribution of the new equilibrium. So there is no violation of the second law. This is a different entropy. This distribution F that we have here is not canonical. So this does not violate the second law because the new Ft prime is not the canonical, is not a canonical distribution. Now comes the crucial step for the second law. You see, because this time evolution here with this Hamiltonian, we just apply Liouville's equations to see how an initial condition for F makes it evolve into a final condition for F, right? Just apply Liouville's equation. You can apply it going forward, but if I were to tell you this distribution, and I told you, well, figure out where this came from, you would be able to recover, by going backwards in time, recover exactly the same distribution here. In other words, the information that was contained in this probability distribution is exactly the same as the information over there. You can recover one from the other and the other from the one. So this probability distribution not only tells you what are the variables that are of interest at the later time t prime, it also contains information about where you came from. What we want now is we want a new distribution F canonical at t prime that is what's going to give us a thermodynamical description. So how do we do this? Using the new distribution F prime, we calculate new xt primes. In other words, if you have microstates that evolve under ht into a new z of t prime, then the old functions x, which were a function of the microstate, will also evolve into new functions x's, and their expected values will also evolve. And so here we're going to have that this guy here evolves to new guys over there. So now we're going to use these guys to maximize the entropy Fg subject to these new guys to get the new Well, the new canonical distribution at time t prime. And two things that we can say about this is that, of course, when you go from the distribution f, the entropy at time t prime that comes from the distribution f at time t prime, and now you maximize an entropy to find the canonical distribution at t prime, then here, oops, no, wait a minute, you maximize an entropy, so it goes like this, and this is the canonical. See what I've done here. This distribution, f canonical at t prime, includes this information of those expected values, and nothing else. It is maximally ignorant about absolutely all other variables in the problem. This guy here agrees as to the expected values. That's the one thing that everybody agrees about. It's the same expected energy, the expected number of particles, the same expected values. The distributions, however, are very different. This one contains way more information. It tells you not only those expected values, but it tells you where it came from. This is the one that you can retrace into the past to see where you had come from. This one here, on the other hand, has forgotten all of those details, and so you can't really retrace it into the past. If you try to retrace it into the past, you're going to get another state that has an entropy that's equal to this one. It's not going to go to the initial situation. So finally, what we have is that whatever this new canonical distribution is, it's a distribution that is canonical and describes equilibrium. This is the Clausius entropy at time t prime. So if we're going to now retrace our steps, let's repeat everything that I have said there. What we have is, you have the equilibrium situation at time t. This is exactly the same as the canonical distribution, as the Gibbs entropy at time t. This is the entropy that was maximized subject to constraints. So let me put it like this. Both of these are defined by the same macroscopic variables. Now we allow this to evolve. And we allow this to evolve with a Hamiltonian evolution. Under that evolution, this guy here does not change. This is a new equilibrium. The new equilibrium has, you can define it for variables at t prime, new equilibrium. And so far, nothing, the entropies have not changed at all. But now we do the trick of saying, well, I'm going to forget. I'm going to discard the information that tells me where I came from. It is at that spot that the entropy increases. And this is the Clausius entropy for the new equilibrium. So maybe I should write this as follows. We have these three entropies that describe the new equilibrium. And we have these two entropies that describe the old equilibrium. It is very nice to see the second law, which is this statement that the entropy, thermodynamic entropy increases. By supplying all the intermediate steps here, we can actually see that one, the fact that entropy did not change during the Hamiltonian step is crucial to be able to make the connection between T and T prime. So having the Liouville law that entropy does not change in a Hamiltonian system, in a Hamiltonian evolution, is crucial to understanding, to making the connection between the T and the T prime. Furthermore, the actual increase in entropy only occurred at the final equilibrium. It had nothing to do with what was going on in this process. The actual increase happened when you went from a distribution that was not canonical and you discard information in order to have the distribution be canonical. This distribution over here, F, included information about the x's, and all sorts of other information as well, where it came from, the memory of where it came from. Here we have the same x's, but nothing else. So the actual increase in entropy, the entropy increase happens when we restrict ourselves to a thermodynamical description. That's the crucial word there. When you were describing, say, this F here, this distribution for the late equilibrium, this is not a thermodynamical description because it is not a description just in terms of the thermodynamical variables, but also in terms of all sorts of other weird features of that probability distribution. When we just have a purely thermodynamical description, that's what enters into the calculation, and you're maximally ignorant about everything else in the description. So a weird conclusion of this is that the second law, and I write it down because this is highly heretical, is not a law of nature. It's not a law of nature. It is a law of the models that we construct to describe certain processes that are interesting to us. The world, the system has 10 to the 23 atoms. The fact that we restrict ourselves to half a dozen is just because for our own selfish human purposes, those are the 5 or 6 variables that we manage to control in the lab. Nature couldn't care less about how many knobs you have in your laboratory. So the second law is not a law of nature. It is a useful, yes, law for modeling. It's a law of models. Nature doesn't care about models. We do, right? So this is a very anthropomorphic concept that's coming into the picture. It's a useful law for models to describe, or that describe, some processes that are of interest to us. Models us. A lot of what our purposes and interests is coming into this interesting presumable law of nature or science of nature Think about it. It's kind of amazing. It's not just nature by itself. It's how we describe nature. Well, one of the things that's sort of amusing about this is that it is very common to start hearing that it is in quantum mechanics that humans have started to come up with theories that are not just theories of the external world, but also theories that include us, the agents, the observers, in the picture as well, right? That is true. But if you actually see how this is being phrased, you see that there is an aspect of it that's already appearing in thermodynamics. And the real reason is that in these theories, what these theories have in common with quantum mechanics is that they are probabilistic theories, and entropies are involved for the purposes of inference. So thermodynamics has, in a sense, or statistical mechanics, has a lot in common with quantum mechanics in that sense. Before I stop here, I would like to make a couple of comments. One comment is that it is sometimes said that the second law drives the system to equilibrium. That the system reaches equilibrium because it wants to satisfy the second law. Now, from what I have just said, it should become a little bit clearer now that this is nonsense. If anything, it's the other way around. You need to have the notions of equilibrium in place in order to even be able to talk about the second law. The second law only refers to entropies of equilibrium states. So if you didn't have equilibrium, you wouldn't even have a second law floating around. So in the same sense, you have a gas expanding. Does this mean that its entropy is increasing and therefore it is expanding because it wants to obey the second law? A gas expanding is not in violation of the second law, but not because its entropy is increasing or whatever. In fact, if you think of the gas as just expanding, and you have the probability distribution of the initial state, and you apply Liouville's equation and you allow it to expand, you are going to be in a situation analogous to this one, where you just have the system start with an initial state and you allow it to expand forever, and the entropy is going to be totally constant, nothing increases, and it will never reach an equilibrium, and that's fine, the gas doesn't care. A gas that is expanding need not, well, violate or agree with the second law. It's neither one nor the other. The second law is completely silent about a gas expanding or about the universe expanding. The second law does not apply to those situations. Very good. I think it's time to stop now. What I would like to do in the second part of the class is come back and talk a little bit more about the second law and discuss, comment upon what the second law actually implies. See you then.